All right, in today's class, we did a crash course in circles. So we covered a lot in a very short period of time. We started off by just kind of identifying, hey, here's some different words, some different features that show up in our circle. A couple that I want to highlight, diameter is just the width of the circle, right? Line passes through the center, gives us the width or height or size of the circle. The radius is just half of that, right? Our diameter is just going to be equal to 2 times the radius. The two that we're going to kind of focus on today are chords, which is just any random line throughout a circle. It could look like that, could look like that, could look like this. It could be the diameter. Any random line through our circle is a chord. And an arc is going to be like the crust of a pizza slice, right? Just a portion of the outside of our circle. Then we also have the circumference, which is our entire perimeter. There are no sides to a circle, so it's called a little different thing than perimeter. It's called the circumference. And finally, sectors and segments. And if an arc is the crust of a pizza slice, then a sector is that entire slice of pizza. All right, and sector is going to be the focus later in our notes. So with everything today, we are just doing a crash course in circles. So some of it's review, some of it's brand new. We're doing a formula example. This first one, area of a circle, a equals pi r squared. It's as simple as using that formula. So in this problem, we have radius of 6. So our area is equal to pi times 6 squared. Now, oftentimes when we're dealing with circles, we want to leave things in terms of pi if we can. So one way to simplify this would be 6 squared is 36. So we could have our answer as 36 pi. Or we could actually use our calculator, come up with 36 times pi, and that would give us 113.10. That is another potential answer there. So we can also use this area formula here. Notice how it shows up here and shows up here to calculate the portion of a circle or a sector of a circle. So these two formulas, one in degree, one in radians, calculates our area of a sector. Now remember that the 360 degrees comes from one full rotation around our circle, and so does that 2 pi radians, right? One full rotation around our circle. So what we're saying when we have this formula is we're creating some fraction, angle over 360, and then we're multiplying it by the entire circle. Same thing with radians, angle over 2 pi multiplied by the entire circle. So how this comes into play in this example problem is we have this sector shown here by 115 degrees, and it's got a radius of 8. So our area is equal to that angle, 115 over 360. And we just go times pi times radius squared times 8 squared. Now this one, we don't need to get in terms of pi. It is going to be a messy formula. One thing I like to do is I like to throw parentheses around my fraction to make sure that it goes in correctly into my calculator. And if we do this problem, 115 divided by 360 times pi and times 8 squared, we should get 64.23. And since this is an area based on centimeters, we'll have centimeters squared as our units. All right, the next problem. Now we're talking about the circumference of a circle. So again, this is going to be that perimeter around the circle. This is equal to 2 times pi times r. So if we know the radius, it's as simple as plugging it in. We have c equals 2 times pi. In this case, we have 6, so times 6. And if I want to leave that in terms of pi, I have 12 pi. 6 times 2 is 12. We can leave that pi alone. Or we can plug that into our calculator. 12 times pi, If we want to get rid of that and have a decimal answer, we would get 37.70. Similar to our sector area, we can find what's called an arc length. And this is the kind of crust of our pizza. So if we have that same slice we took out in example 2, and we wanted to measure the length of that arc, we can use this formula. And the same principle applies, right? We take a fraction of that angle and we multiply it by a whole, right? We multiply it by that entire circumference. Notice how that's our circumference there. That's our circumference there. And we are multiplying by some portion, some fraction, some ratio. So in this problem, L equals, this is degrees, so we use our top formula, 115 over 360 times 2 times pi, and our radius is 8. And if we go ahead and punch that in our calculator, again, I'm going to throw some parentheses around here to make sure that I do my order of operations right. 115 divided by 360 times 2 times pi times 8. We get 16.06 as an answer. Now, just a few more things to cover. And again, we are throwing a lot at you. It is a lot of circle information in one day. We have this theorem that happens with intersecting chords. When we have a chord like AB intersecting with a chord like CD, they create 4 separate segments, right? This A segment, this B segment, this C segment, and this D segment. And if we multiply them together, A times B and C times D, those two values should be equal to each other. So let's see how this comes into play. In example 5, we have 2 chords that are intersecting each other. We know that one of the chords is 12. We know that one portion of our chord is 12. Another portion of that same chord is 7. And if we go to that different chord, we have a short leg of 3. And we have this long leg, which is unknown, which let's call this x here. If we then apply this formula over here, A times B equals C times D, we get 12 times 7. There's our A times B. And that should be equal to 3 times x, that C times D. If we do that problem, 12 times 7 is 84. That's equal to 3x. And we can simply divide out by 3 on both sides to get our answer, which should be 28. And that is what that x value is equal to there, 28. Now, our last 2 kind of things are a little funky. And they're dealing with something called inscribed angle. An inscribed angle is going to be any angle that is centered on the outside of the circle. Notice how my point here, where the angle's at, hits the outside of our circle. If we have an angle like that, and we also have an angle that matches the same points, the start and end points, and runs inside, but only goes to the center of the circle, then this center angle is 2 times whatever this inscribed angle is. Let me say that again, just to make it clear. We have some angle that starts here, runs all the way across, hits the outside of our circle, then runs here. Notice these start and end points, right? I'm going to label one of them orange, one of them green. Okay? If I draw another angle that goes through the center, but hits those same endpoints of orange and green, then that center angle is 2 times whatever A is, or 2 times whatever the kind of inscribed angle is. So in example 6, we have PRQ, which that's our inscribed angle. So that's the same one as this angle here. And we have POQ, which we're trying to find out, right? What is POQ? that is the same as kind of our central angle here. So we want to go and take 2 times whatever this 62 is, which gives us 124. And that is going to be our answer, 124 degrees. We could also work the other way where we could take 124 and divide it by 2 to get to 62 if that's what the problem was asking. And last one here. This is dealing with inscribed angles that share the same endpoints. Let's look at this. I have this circle up here. I am going to trace from a starting point to my angle center back out to an endpoint. Notice how we have 1 point here, 1 point here. Okay. If I trace any other angle around that circle to the same start points, like this one here, then my angles are going to be equal to each other. Let me do that again with a fresh circle here. Have a circle. And if I draw an angle here like this, and let's say that angle is 20 degrees. Any other angle that I draw with the same endpoints, let's say it's this and this, that angle is also going to be 20 degrees. Let's see how this plays out in an example problem. In example 7, we're given a lot of information, and ultimately we're trying to find this angle CBX. So we're trying to find this angle here. What's our unknown here? We know one of our angles in our triangle is 85. Okay, we know that. Another angle in there is angle C, but we don't know what that one is. I'm going to kind of start highlighting this one in blue. If we can find this one, then we can use our triangle angle sum idea where they all add up to 180 to solve for that missing angle. So if we look at triangle A, or angle ACB, that shares the same endpoints A and B with triangle or angle ADB. So that means that this 32 over here also must be the measure of the angle at C, 32 degrees right here. And then if we have that, we can find that missing angle, this angle B here, as 180 minus that 32 minus that 85. And if we do that, 180 minus 32 minus 85, we get a value of 63 degrees. And that is what this angle at B is, 63 degrees. Now, we could apply that same thing to finish out all of our angles if we wanted to. We're really done with the problem, but if we wanted to, we can notice that, hey, this angle at 63 starts at C, cuts through B, and goes down to D. Well, that same angle shows up if I start at C, go to A, and go to D, which means that that angle at A is also 63 degrees.